So far, we have seen that the effect of rotation of coordinates through an angle theta about an axis n hat can be thought of as an operator un theta acting on the ket describing a system, or equally well as un dagger theta o un acting on every operator describing the system. Remember, in one case is the ket which gets changed, in the other case is the operator which gets changed. And just to stress once again, we are talking of passive rotations where the system stays the same, it's only the coordinate system which gets rotated. Now, we have already seen that for an infinitesimal transformation or infinitesimal rotation, the operator un theta is going to be identity plus a first order correction which is proportional to the infinitesimal angle of rotation and multiplied by an operator which is just the angular momentum component in the direction of the rotation axis. We should now can ask ourselves, with just this much knowledge, can we figure out what will happen when the rotation angle is not infinitesimal but rather finite? Well, we can, and that's due to a very simple basic result. If you want to rotate through an angle theta about an axis, you can do that in one go, or you can do that in n steps where of tiny angles where the angles add up to theta. In particular, you could make n rotations about the same axis n hat through an angle theta by n, and that will ultimately lead you to a total rotation of theta. And because of the fact that when you apply successive rotations one after the other, the successive transformations on Kets also gets applied one after the other, you end up with this result, that un hat theta is actually the same as un hat theta by n, the transformation for a small angle raised to the power n, that is applied n times successively. Now, if I take n to be large enough, then the angle theta by n becomes very, very small. So small, in fact, that in the limit when n goes to infinity, it's only the first order correction that matters. So, what we end up with is un theta is the limit as n goes to infinity of un hat theta by n to the power n. But in this limit, un hat theta by n is nothing but the identity plus I by h cross times the angle theta by n times the component of the angular momentum in the direction of n hat. Now, this limit is actually a very familiar one. It's a familiar one from basic maths. In case you have forgotten that, let me just make a brief recap of that. Let us recall from elementary mathematics that 1 plus x by n to the power n can be written down using binomial theorem in this form: 1 plus n by 1 factorial x by n plus nc2 n into n minus 1 by 2 factorial into x by n whole square plus nc3 into x by n whole cube, and so on. Now, you have a power of x in every term and a corresponding power of n in the denominator, and we can try cancelling out this with the n's that appear in the NCR factors. So, in the first case, the n just cancels. For n into n minus 1 by n square, one n cancels. You are left with 1 minus 1 by n. For the next one, you are left with 1 minus 1 by n into 1 minus 2 by n, and so on. And so, this is finally what 1 plus x by n to the power n looks like. Of course, there are more terms to this. N plus 1 terms to be precise. That's exactly the number of terms in a binomial expansion. Now, if we take the limit n goes to infinity of this, then this 1 by n becomes negligible compared to 1. Similarly, 1 by n, 2 by n both become negligible compared to the 1. And so, the limit simply becomes 1 plus x by 1 factorial plus x square by 2 factorial, this becoming 1, then x cube by 3 factorial, and so on, which is our familiar exponential function. So, 1 plus x by n raised to the power n in the limit n goes to infinity becomes exponential of x. In fact, this is exactly the way the exponential function was introduced historically, as an answer to the question, how much would an unit principal become for a rate of interest x if it were compounded arbitrarily many times in a year? The history is fascinating. You may want to look it up. Now, however, you may have a nagging doubt at this point. After all, we are dealing with operators and not numbers. So can we use the same argument? As you all know, binomial theorem a plus b for a plus b whole to the n may very well not work for operators because the operators will not commute. So a plus b whole square, for example, is not in general a square plus twice ab plus b square. It is actually a square plus ab plus ba plus b square. However, notice that all you need for the binomial theorem to work is that a and b commute. And if we are using identity plus an operator by n raised to the power n, then there is no reason why binomial theorem cannot be used. And hence, modulo some mathematical rigorous issues with rigor as to the limit as n goes to infinity, this proof works perfectly well when you have an operator sitting instead of x. So 1 plus a by n to the power n, where a is an operator and 1 is really not 1, is the identity operator, in the limit n goes to infinity does give you the exponential of the operator a, which, remember, is defined to be identity plus a square by 2 factorial plus a cube by 3 factorial and so on. So coming back from that mathematical interlude into elementary or high school mathematics, we restate that the limit n goes to infinity for this, sorry, I am at the wrong place. Yeah, the limit n goes to infinity of this is nothing but the exponential operator, exponential of I theta by h cross n hat dot j. So we should be able to figure out what a rotation operator is if I knew what the j operators are. So the angular momentum operators completely determine the way in which a state of a system or the operators of a system, either way, respond to rotation of coordinates.